Morning, everybody.
Morning.
We sorted out the universe this morning, apparently. We got the last exam on the correct date, right?
Yeah.
Okay, thank you. So that just means there's slight date problems with the Excel calendar. I may or may not fix it. It'll be fun. Okay, so I think in the calendar it says that we're supposed to do chapter 22 today, and then we only have one day for chapter 23, which will be this. Okay, so we got today, we've got Thursday. What's happening next Tuesday? Review. Okay, and then we're taking the exam a week from this Thursday.
Yes.
Okay, so, and did I post the topics this morning?
Yes.
So, past me was amazing this morning. I'm not sure that current me is going to be able to keep up. So that's all coming to a head, right? And yeah, this exam is going to be hard, not because I made it hard, but just because it's hard, right? It's right-hand rules and all that kind of stuff. So we'll get there. We have a week to get there. All right. We left off, I think, wasn't I launching stuff in class? Right, with the railgun launcher. Okay, that's called Thompson's flying ring. So we were sort of, that was an example of motional EMF, this ability to not only generate electricity by moving something in a straight line, but you can reverse that, right? Use electricity to move something in a straight line. But this gives rise to something else that we need to connect up here. Faraday's law is this statement of, please tell me it's showing something up there, right? Okay. It's hard to move my neck today. So I gotta turn the whole body. Maybe we'll see what's going on. Okay, so we have this change in flux, right? That whole terrorizing, increasing, into or decreasing out of, or whatever's going on, right? Okay. And then we've got this minus sign. That is the Lenz's law, right? Part with all the right-hand rules and terror in there. This voltage, I haven't really talked that much about it, right? It's a voltage that gives rise, and because of Coulomb's law, if you have a voltage and you have resistance, say, in a wire, there's going to be current. It's part of the package deal, right? But what is the shape of that voltage? Which is kind of a strange question to ask, but like, yeah, like, is it a line? Is it a circle? What is this voltage? What have we been doing for like the last couple days? We're always finding the current, right, in a what? Not just a wire. In order for Faraday's law, in order for Lenz's law to be taking place, it always needs to be a coil, right? A loop of some kind, right? So the shape of this, right? We talk about the current because it feels better to like say, well, the current in a wire. That's the flow of the charges moving around, right? And voltage doesn't have a direction. It just has a magnitude, positive or negative. So the current does, which means the voltage in this wire, right, needs to be sort of going high to low in a circle all the way around it. But voltage and electric field are related to each other. When we first talked about electric potential, it was all about this connection. It was this idea of taking the electric field, taking it one step further so we didn't have to worry about vectors anymore. And we could just kind of do this scalar idea of voltage, and then we could like build electric circuits and all that kind of stuff without having to worry about the fields. Well, we're bringing the fields back. Insert, was that Justin Bieber reference here? Okay, so what would the electric field look like in this wire? If the current is going around counterclockwise, what direction is the electric field pointing? We need the charges to move and follow this path. No. What? What is it that charges? So like if I have an electric field that say is doing this, right? And I say that these are my electric field lines, okay? And I drop a positive charge right here, what's it going to do? It's going to follow the lines, isn't it? Okay? So if I drop a charge here, it's going to go in a circle, isn't it? Okay? So we're going to have an electric field that looks like a circle. So up to this point, we've done electric fields that are basically sort of lines, right? They start on positive, they end on negative, right? And now, with Faraday's law, we have a circulating electric field. Is there a field that we've studied that forms closed loops and circulates? Okay, so this is not a magnetic field, but it is a circulating electric field that causes a magnetic field. Because with current flowing in that loop, no matter how we got it, whether we actually are like making it happen with a battery or it's been induced by Faraday's law of electromagnetic induction, it doesn't matter. If there's current flowing in a loop of wire, right-hand rule tells me the direction of the magnetic field depending on the direction of the current flow. So electromagnetism is this concept and idea that electricity and magnetism really can't be separated from each other. We've taught it, right? We've taught you electric fields, and then now we've gone into magnetic fields, but it's all coming together now. In that when you generate when a changing magnetic field, a changing magnetic flux causes a voltage to happen, that voltage has an electric field associated with it that in turn causes a magnetic field to happen. And these concepts and ideas, especially in electrodynamics where things are moving and changing, are completely connected and coupled together. Okay? So this gives rise to a phenomenon referred to as eddy currents. Okay? And to demonstrate what this is, does anybody know what an eddy is? Like think about like a river. What's an eddy? If you see an eddy in a river or an eddy in a pond or in a body of waters, did you guys know that term? It's like a little miniature whirlpool. An eddy is like a sort of a circulation of just a little part of the water. If you've ever had the opportunity to swim and you like kick your feet, the water will sort of eddy around where your feet. It'll splash a lot, that's turbulence, but an eddy is more of a smooth sort of circulation. Eddies exist in any fluid that is being pushed around by some physical object. You'll usually get these eddies. Anyway, an eddy is this circular sort of flow of water. Well, in solid metals, you can get eddy currents. Okay? So this is a piece of aluminum. It is not magnetic at all. I have a very strong magnet right here, and it doesn't care. Okay? So, and then I'm going to put this pendulum it looks like a spatula, doesn't it? Okay? So a little quiz now. Okay? So this is a hair comb. Don't use this in your hair. Okay? If this is a spatula, then what is this? It's a pancake turner. It's a technical term, cooking with Mr. Balogh. Okay? That's a class that's been requested by past students. Okay? This is a spatula. How do you know? It's solid. Okay? And then this is a pancake turner. There's another one called a fish spatula that's elongated, that has holes in it. That's different. All right. So I take my spatula here, right, and I put it on the end of my boom, right? I've set up a pendulum, right? Okay? And you can see that there's some friction there, right? I mean, it's going to slow down. It's going to stop moving here in a minute or so, right? But not a whole lot of friction. Now what I'm going to do is I'm going to cause this piece of aluminum to swing through the magnet. I'm going to try and put this right in the middle of the magnet so it doesn't hit, okay? And Get it? Doesn't have to be lined up perfectly, but I do like it to be lined up perfectly. Okay, so now with the magnet in place, I want you to note how long it takes for it to stop swinging. Oops, something wasn't tight. Here, come on. There we go. No, gonna hit. There we go. What? I'll do it again. Okay, it's not hitting. Toby, right? It didn't hit the magnet, right? Okay, it's just swinging in, right? And stop it. I'll pull the magnet out, okay? And I'll swing it again, right? Okay, so what have you just witnessed? What is this thing? Can anybody think of a real world application of what just happened? This is a magnetic brake. Okay, this is a brake that requires no physical contact between the brake pad, or the disc for lack of a better term, right, and the brake pads. In a regular brake, you have a disc that's on the wheel of your car, and then pads come in and hydraulically squeeze on that disc to slow your car down via friction. There's no touch here, right? Okay, and so there's no friction. There's no material to ablate or remove in that process, and yet we got it to slow down. Heat is generated because inside of this metal spatula, we are forming eddy currents, currents that circulate around within the metal. And because this metal is solid, there's a lot of currents, right, that can be made. So here, we take exactly, so it's the same size, right, same dimensions, everything like that. It's just we've hollowed out some slots in this one. Yeah, Chris?
So then the eddy currents make magnetic fields that solid.
Yep, that directly oppose a la Lenz's law, right? What's going on here? So I swing that one in, right? You can see that it stops, but not quite as fast, right? There's a little bit like it tries to get through and then comes back, right? So this one has been made lightweight, right? There's less material, but still about the same stopping power. And then we've got the hair comb here. Any predictions? Okay, so why is this one not as effective? You can see it's affected, right? It is slowing down faster than friction alone, but it wasn't nearly as much as the other one. Why?
The eddy currents are just escaping.
We can form really tiny eddy currents in this one, but what can we do with this one? We could make a really big loop, right? Because it closes off on the edge there. And then in here, we can just make big, small, and everything in between, right? So it's the most effective. So as the pendulum swings in, it sees or experiences increasing magnetic field. So is the flux increasing or decreasing? It's swinging in. It goes from no flux to lots of flux. So that's an increase, right? Okay. What does Lenz's law have to say about that increase? It wants to oppose it, right? So we'll increase the opposite direction. So as it swings in, it'll start like opposing the change, and so it'll like push itself out, but momentum carries it through. And now it's halfway through the magnet, and it starts to leave. Well, as it starts to leave, is the flux now increasing or decreasing? It's now decreasing, and it says, wait. I want to get back in, right? And it start, right? So no matter what happens, as it enters or as it exits, it's getting slowed down. On entry, it's getting pushed out, but on exit, it's being pulled back in because of Lenz's law. You can take advantage of this by not only making a magnetic brake, but connecting your magnetic brakes to the electrical systems of, say, an electric car. And as you slow the car down, you're generating eddy currents in the brake, and those are currents that can be captured in wires and then used to charge the battery, and that's regenerative braking. Okay? So the thing about internal combustion car is there's inefficiencies in the engine which technically could get improved if we changed how we manufacture things, but car companies don't want to do that because they say something about money and stuff like that. But the inefficiencies of the engine aside, okay, an internal combustion car uses gasoline energy to get up to speed. So you change chemical energy into kinetic energy, and then what do you do with all of that kinetic energy to stop? You turn it into heat. You just heat up the atmosphere. More global warming, thank you. Okay? An electric car uses electric energy to turn that into kinetic energy, and then what does an electric car do with the kinetic energy? Turns it back into electrical energy, right? And you end up capturing about 80% of the energy you use to get going to send back to the batteries. There's still losses to heat and all that kind of stuff, but at least you're not just throwing it away to thermal energy, right? So that's one way that, because batteries are a really kind of poor energy storage system. They're not nearly as energy dense as a gallon of gasoline is. And so a electric car that's got like a 300-mile range is able to do that, not because the battery can actually make it go 300 miles, but because they're taking into account regenerative braking and all that kind of stuff. So, what was that? So yeah, a lot of evidence that hybrids don't work. That hybrids are a consumer-facing Band-Aid that helps people get over something called range anxiety. It's this very real psychological phenomenon in the ownership of electric cars where people start freaking out about the fact that they can't go very far in their car. The fact of the matter is 95% of daily driving is done within 20 miles of a person's residence, right? And that unless you have a job that specifically has you, say, traveling to long-distance job sites or something like that, most people don't need to drive more than 20 or 30 miles in a day, right? And so if you have a 300-mile battery, you're more than covered, right? Where it comes into the anxiety part is, well, what if I want to take that road trip, right? What if I want to go to the coast? And it takes a while to charge the battery. It can take like an hour to fully charge an electric car's battery from 0 to 100%. Yeah, those are all truisms, right? But in the end, if you want to take a road trip and you have an electric car and you're afraid it can't take 800 miles and it's going to take an extra hour, just rent another car. Especially if you don't do road trips that often, right? You'll end up saving money, saving the planet, recouping your costs, like all that kind of stuff. I am an electric vehicle owner. Of course I am. I'm a physicist and a hippie, right? And, right, I can tell you that I had range anxiety for about 2 weeks. Okay? The best thing I ever did in my car was turn off the display that told me how many miles I had left. I switched it to a percentage of battery remaining, and I've never worried about it again. My car just tells me whenever it needs to charge, I pull over, I charge it. I'm old. And so I need 20 minutes. Every 2 hours, I need 20 minutes to just stand up and walk around and go to the bathroom and get all the kinks out. My car goes from 10 to 80% in about 15 minutes. It doesn't go to 90 or 100, but 80% is enough to get me about 250 miles down the road. And my bladder is good for only about 90 miles. So it's really good.
A lot of road trip routes that are commonly taken usually have a lot of charging.
Yeah, all charging stations all over the place. It's really become a solved problem now. The problem is cost. Electric vehicles cost more in their upfront purchase, right? And it's out of reach for many, many households, which is completely understandable. But as more and more electric vehicles get produced and get on the roads and all that kind of stuff, those costs are coming down, right? So I'm in favor of electrifying everything. Cars, trains are already electric. Airplanes, that's a hard one. Deans, high school students, electrify everything. Okay, just do it. She wasn't in the room. That was a joke that didn't land very well. But all right, so again, direct practical applications to the stuff that we're learning, right? Okay, you basically saw Lenz's law in front of your very eyes, right? Tied in with everything else. Okay, what's a transformer? Speaking of practical things, they are more than meets the eye.
You can switch between AC and DC.
We're not talking about this kind of transformer, right? Okay, we're talking about this kind of transformer. Now, strictly speaking, this is a transformer. Okay, this is a transformer rectifier. Okay, so there's a difference. Okay, the thing that you plug your phone into or your laptop or whatever, right? Okay, it does two things. It turns AC into DC. That's a rectifier, changing AC into DC. We're not talking about that right now because that requires quantum mechanics. A transformer takes high voltage and turns it into low voltage, or vice versa. The transformer you see in your neighborhood or anywhere that there's power lines, if you look at the power lines, every once in a while there'll be this little canister or something that kind of looks like it. If the power lines are underground in your part of the city, you'll see a green box every so often, right? Green spray painted box, okay? It's usually one of two things. It's either internet networking equipment or a transformer, okay? And what transformers are doing is solving a problem. Getting electrical power and energy into households is difficult. It's difficult on a lot of different levels, and I am not going to speak to the economics of it because I'm not a business person. Money doesn't I'm not influenced by money or I don't think in terms of money, right? It's and I am fortunate enough to not really have to worry about it. I worry about it because I have kids in college, but that's a different story, right? But this is not about the economics of it, although partially it is. This is more about the technological problem of sending large amounts of electrical energy from a power plant to the point where people need to use it. You want to be able to generate it, enormous amounts of it, but you don't want to pipe the entire power plant directly into your home. Okay, that would be overkill, right? So how do we distribute? How do we send it efficiently and all that kind of stuff? A transformer solves this problem. I'm going to try and explain all of this now in a way that hopefully kind of comes through. This is not what they actually look like on the inside. This is more of an idea that will help you wrap your brain around what's going on, okay? A transformer is it's a metal bar that has two different windings wrapped around it. Again, the actual engineering of it differs, but the idea is that there's a primary coil and then a secondary coil. And they have two different windings or number of turns. So we might say the number of turns in the primary and number of turns in the secondary. If those two things are equal, then the transformer won't do anything. Voltage in equals voltage out. However, if you play with the ratio, if you increase the number of turns in the primary compared to the secondary, or vice versa, we can affect what the input and output voltages are. Your book uses this equation. There's two equations I'm going to give you, and then we'll investigate how to use them, okay? That's the ratio of the voltage in the secondary compared to the voltage in the primary. And it turns out, by the way, you use Faraday's law to derive all of this. Transformers do not work without Faraday's law of electromagnetic induction. But it turns out the ratio of voltages is exactly equal to the ratio of the number of turns. Okay? Notice the order there. Secondary is on top, primary is on the bottom. while we're here, let's talk about the currents, because voltage and current go together, right? Ohm's law. This turns out to be a reversal, and we'll talk about that in a second, okay? I do kind of like to talk about, like for me, this is what your book writes. I tend to write my transformer equations like this. Right? All I did was multiply both sides by voltage in the primary, right? Because typically we know what the voltage in the primary is. For example, your phone charger or your computer charger, right? The primary side, the wall side, what's the voltage that comes out of the wall?
120.
It's 120, right? But the USB port on your phone only needs 5 volts. The 5 volt standard on the USB bus. Any higher than that, devices are going to freak out, okay? So you need the power brick for your phone to adjust that voltage, and it does it via a transformer. Now this happens to be what we call a step-down transformer. We're going from 120 volts down to 5 volts, okay? And so we've stepped down the voltage. Step down, step up and step down transformers are always in reference to the voltage, right? At the power plant, they produce electrical power at around 50,000 volts-ish. That's what a generator in a power plant is designed to do, 45 to 50,000 volts. And by the time it gets to your house, we want it to be 240. But between the power plant and your house, they actually send it at 500,000 volts along some distances. So we're constantly playing this game of different voltages, which I'll explain in a minute why we do that. But we have to be able to trade. We got to be able to go up. We need to be able to go from like 50,000 volts to 500,000 volts. By the way, what would the ratio there be? If we're going from 50,000 to 500,000, it's 10, right? It's a ratio of 10 times, right? In order to get that to go up. So that's what we refer to when we say step up or step down. So like if the voltage in the secondary is bigger than the voltage in the primary, is that a step up or a step down? No, this is step up. The secondary is bigger, right? Okay. But if the secondary is smaller, then this is a step down. Just terminology, right? About what's going on. But energy must be conserved, right? Like we can't break energy conservation. So if the voltage is changing, is the current changing? Yeah, right? We've got another equation over here that says, right, the reverse. If you step down the voltage, if you go from 120 to 5, then the current goes up. Okay? So voltage goes down, but current goes up because to conserve energy, power stays the same. Power, like power in the primary and power in the secondary, are exactly the same. It's voltage and current that we are playing with in this situation. All right, so let's do an example. The transformer calculations are not supposed to be difficult, okay? It's merely just a matter of like making sure that you know which is primary, which is secondary, and what you're looking for, okay? So what have they told us about this transformer, right? Okay. What is the 120 at 5 amps? What are those? Voltage of what? What's the 120? Primary or secondary? Primary. That's a primary or input voltage, right? What's the 5 amps? Primary current, right? They tell us that the number of turns in the primary is 800, right? And the number of turns in the secondary is 200. Then they want the output voltage and current. What are they asking us to solve for? Voltage secondary and current secondary, right? So we whip out our equation. I like to write it like this. Did I write it right? Yep. Okay. So I know the voltage in my primary, 120. I know the number of turns in my secondary was 200. I know the number of turns in my primary was 800. 200 divided by 800 is 1/4. Is that right? And 1/4 of 120 is 30. Did I get that right?
Yes.
So, was this a step up or step down transformer?
Step down.
Step down. We started at 120 and we went to 30. Okay? So how do I find the current in my secondary? I always have to check this one because I get it wrong because it's reversed. Okay? That's just a copy paste from this equation right here that I solved for current in the secondary. All right, so let's see. Current in the primary was 5 amps. Number of turns was 800. So this is a factor of 4, right? 5 times 4 is 20. 30 volts, 20 amps. Multiply 120 times 5 and 30 times 20, and you get the same number. Okay? So power and energy are conserved. What is adjusted is voltage and current. Transformers only work using alternating current systems. You must have a change in magnetic flux through the coils in order to communicate between the coils. DC will not do it. DC is fantastic for microelectronics. Microelectronics don't like alternating current that much. Can't really, it's hard to do work with AC. It's possible, but it's a harder proposition. So things like computers and microelectronics and simple circuits, they want DC, which is where we need to convert AC into DC, but again, requires quantum mechanics. But in terms of the actual power that's being delivered, that stays the same, but we want to be able to adjust voltage and current because current too high, say in a battery or a processor or a graphic card will melt the contacts, ruin the device, all that kind of stuff.
So have you ever explained why or is DC like easier to transmit?
No, so we're going to talk about that right now, okay? Because it turns out AC is way easier to transmit, okay? Way easier, okay? So I demonstrated for you the generator last time, right? You turn the thing and the light bulb lights up, okay? We're turning a coil in the presence of a magnetic field. We're using Faraday's law of electromagnetic induction. You can't do generators and motors without it, okay? By the way, does anybody know the difference between a motor and an engine? Motors are electric. Engines are fuel, gasoline or oil or something like that. So provide mechanical motion. Turning this coil in the presence of a magnetic field generates electrical output. But because that coil is turning within the magnetic field, we're going to get this oscillation or flip in direction of the voltages and currents that are made in that coil. Remember, changing flux as you change the angle. We go from, remember, it's B times A times cosine of the angle. Well, that angle can go from 0 to 180 to 360. What happens to cosine as it goes from 0 to 180? What's cosine of 0? 1. What's cosine of 180? -1, right? It flips direction. And then as you come back from 180 back to 360, goes back to 1. So you're getting this flip, right? It's just a natural thing that happens in a sine or a cosine function. And that's what is output from a generator naturally. Generators naturally make alternating current. which is good because alternating current turns out to be something that's easy to transmit. Now, instead of having people or monkeys or squirrels turn the loops, right, you can have steam turbines do it. Okay, so we're still in the steam age. We're still boiling water to make stuff. Okay, right? And you can start connecting together a grid, right, of interconnections and all that kind of stuff. So again, like, why? Why step up? Why step down? Why not just have everybody running generators in their backyards? All that kind of stuff, right? Well, this is going to circle back to an equation that I gave you a while ago, okay, in the last unit, in fact, okay? And it was this one. Does anybody remember what I called this one? This is obtuse, and you don't have to worry about it if you don't remember. It's power lost, okay? This is the power lost equation. Called that because resistance takes electrical energy and transforms it directly into thermal energy. It's the friction of electricity, okay? And so we call it power lost because if you have resistance anywhere in your system, you will lose some of the electrical energy to heat. And the amount of energy per time you lose is given by this equation.
So then with it going up and down, there's points where it's less.
No, you're close. It's still going to go up and down no matter what. But notice how power lost scales. There's really nothing you can do about resistance. Resistance is a function of length of wire and diameter of wire, right? So if you want to send electricity long distances, you can't really help the distance. It is what it is. So you can make your wires bigger. Bigger that cross-sectional area, the less their resistance, okay? But again, there's kind of physical limits to this. Yeah, you can make a wire that's as big as a sewer pipe, but no, good luck hanging it anywhere, right? Okay, it's just not going to happen. Wires will stretch under their own weight, and so there's engineering limitations on what you can do there.
We try to have it.
But there's something else that causes the power loss to change even faster.
It's the current.
It's the current. It goes as the square of the current.
So that's why we transmit it really high voltage, because the current is really low.
Low, right? Remember, it's a trade-off, right? A high voltage means a really low current for the same amount of power transmitted. Power stays the same. So if we can transmit the electrical power and energy per time over long distances at very high voltages, that means the current is really low. And if your current is being measured in milli or micro or nanoamps on the long distance part, okay, then you're not losing too much energy to just heating up the wires. But it's really bad form to send 500,000 volts into somebody's kitchen. Okay? Right? Okay? So you've got to be able to reverse it on the other end, right? Step up. And as a matter of fact, we've got megavolt lines now in California, right? They were 500,000 volt, then they went to 800,000 volt, then to 900,000. Now we're at megavolt on the, especially I think the transmission line that's over by the I-5. The one that's over here by the 99th still, I think, is only an 800,000 volt line, only. Okay.
Yeah,
Good.
just don't touch that.
Yeah, good friend of mine is a PG&E lineman. It's his day job to go and mess with the high voltage lines, right? Okay. He and I talk a lot about electricity, but we also talk a lot about death. Anyway, so send it at high voltage, low current, and when it gets to the town, you've got to start stepping it down. And so if you've ever seen these areas in Fresno that are, they have the big fences around them and they say danger, high voltage, and it looks like a place where the aliens are supposed to land, right? Okay. Those are substations, okay? Those are places where the high voltage is coming in and they're lowering those voltages, increasing the currents, right? Voltage goes down, current goes up. They take it from 500,000 volts down to about 50, and then 50 to 20, and then the 20 is what runs all over the neighborhoods. The stuff that you see on the power lines is about 15,000 to 20,000 volts, And then you'll see a transformer on one of the poles or one of those green boxes. And one of those transformers can do about 5 to 10 homes, depending on what kind of transformer it is. Okay? And so you're sharing a transformer with several of your neighbors or apartment complex or whatever. And then at the house, the final step takes place. It's not a transformer. It's 240 volts to your house. It comes off the transformer, 240 volts to your house, and at the panel in your house, they'll split the 240 into 120s, right? So you can have both. You can have 240 and 120. All of that is made possible by Faraday's law of electromagnetic induction. Without AC, we would not be able to trade voltage for current. You cannot do this with DC. Stand over here because the lightning might strike. Thomas Edison was a very bad man. He did not invent the light bulb. Okay? His workers invented the light bulb. He capitalized on their work. Okay? Thomas Edison was a good businessman. But from where I stand, good businessman and good person they aren't the same thing, right? And so, like the robber barons of the age, and the current ones of our age, exploiting people was their genius. And there was a scientist by the name of Nikola Tesla, who was a great scientist, but a very bad businessman. And his story is actually very tragic, involves mental illness and some other things. But Nikola Tesla pioneered our modern electrical grid. Without Michael Faraday and then Nikola Tesla's engineering and physics prowess taking Faraday's ideas and making them practical, we wouldn't have the electrical grid we had today. In fact, Thomas Edison was rolling out an electric grid in New York City that was based on DC. Thomas Edison believed, incorrectly because he was an idiot, that DC was better than AC. And it just isn't the case. Like, the physics of it doesn't work. Okay? Not only do the generators naturally make AC, and so Edison had to basically throw away half of his generator cycle. Okay? It just isn't, like, with DC, you need a substation every, is it 500 feet or something like that?
Yeah, it's ridiculous.
In order to keep the power flowing correctly. Whereas AC, you can go 100 miles between substations and be just fine, right? Like it's phenomenally bad. I need to say something political, so I'm going to come over here. Okay. Has anybody heard about the idea to put AI data centers in space?
Yes.
Okay. It is very obvious that Elon Musk does not understand physics. Because there is a basic thermodynamics problem with what he is talking about. Data centers, why are data centers bad?
They produce a lot of heat.
A lot of heat, use a lot of water for cooling, use up a lot of electricity, which drives up costs for normal everyday people, right? Okay. Why are data centers so popular right now? AI, right? Social media, all this kind of stuff, right? Okay, got to have the cloud. So the proposition was, well, let's just put them in space. The problem is for one AI data center to get the heat out that the chips create, you would need something that is roughly 300 times bigger than the current International Space Station. Just in radiators to radiate the heat away. Never mind the solar panels and all that kind of stuff. And I think it was Elon Musk and SpaceX put in saying they wanted to put 1 million of these things in orbit. It's not going to work. Like, physics, basic physics cannot be denied, right? Just because you have a lot of money doesn't mean you know anything.
So I know a lot of the AI stations, they've been using a lot of fresh water and going through polluting it. Why can't they just do closed loops?
Oh, they have closed loops in there, but you still need to be able to cool off the closed loop. And salt water is horribly corrosive to just about anything you put it into contact with. So.
Yeah,
Microsoft tried it, and I think it ended pretty much.
Yeah. Now, I'm a hippie, so I'm going to say what I'm about to say with reservation. There is one place that is really cold, and there's a lot of cold, and we probably won't cause any issues if we put a lot of data centers there. No. Bottom of the ocean.
I was going to say Greenland.
Yeah, no. Bottom of the ocean is the answer. Okay? We don't know a lot about the ecosystems that exist down there. So we don't know what would happen if we started dumping a lot of heat down low in the ocean. Science needs to happen, right? But from this scientist's point of view and the experts I've talked to, it's a better proposition than what we're doing to our air right now, our air and freshwater systems, right? I'm not saying it's good. I'm just saying if you're going to make a choice to build these things out, which is a different conversation, then I pick bottom of the ocean right now. This is exactly similar to very similar to the argument that if humans are going to wipe out a species, we're pretty good at wiping out species in general. But if we're going to wipe something out, I pick mosquitoes.
No.
Yes. No, go talk to your biology teachers. I've talked to so many biologists.
That's like the one thing that we don't care if they die.
Not only we don't care, but fish don't care. Like mosquitoes are food for things, but the things that eat mosquitoes for food have other sources of food.
It's like the one thing.
The ecologists that I've talked to, and I have not cherry-picked my data. I asked basically every biologist I come across, I'm like, what about mosquitoes? They're like, oh yeah, those can die.
My brother, literally his job for years was just making it to where they couldn't reproduce.
Yeah. These programs are working. Like getting rid of malaria is a net positive for all of humanity, right? And malaria is carried by mosquitoes. Dengue fever, Egyptian, whatever, right? There's so many diseases carried by mosquitoes. Just wipe them. That line from Star Wars, wipe them out. All of them, right? I am in a war against mosquitoes. I will do anything to kill them, right? They are the enemy. Talk to the biologists. They'll tell you the same thing. All right. On to chapter 23. We made it through right. There will be no right-hand rules in chapter 23. Okay? I promise. There just isn't. Okay? So, what's going on in chapter 23? In chapter 23, I am going to tell you right now, don't read the book. Okay? Like, I know some of you are like, oh, I've got you, Mr. Balogh. I haven't been doing it for 22 chapters. Normally, I say, you're on the hook for reading the book. This time, no. Because in every textbook, in every physics class, they go too deep for this. And I'm sure that there are physicists somewhere who are not right in the head that like AC circuits. I am not one of them, okay? Yeah, but like seriously, just listen to what I say in lecture for this one. And again, some of you are like, no problem, Mr. Balogh, I've been doing that the whole time. So, no section 0.5, like there will be no homework from it. If anybody mentions a phasor, it's not what you think. A phasor is a rotating vector. Yeah, nobody wants to see that. Okay, right? Okay. So yeah, and the next generation is better than the original series. I will die on that hill too. We are going to do what everybody else does. Okay? All of electrical engineering, all of our power grid, all of our devices, Everything that we do nowadays is based on a lie. And the lie? Okay? Right? We already know how to do DC circuits, right? In DC circuits, we have Ohm's law, right? We got parallel, we got series, we got all that stuff, right? Power, current times voltage, all that different stuff, right? Okay? We all know that about DC, right? In AC, we are forced to do one of two things. Either we jump in and do it for realsies with this sine and cosine, time dependent, all this kind of stuff going on, or we cheat. We cheat and we say, you know what, AC is really just DC if you don't look at it too closely. And then we just do everything in like we would with DC. So that's exactly what we're going to do. This is what electricians do when they come and service your house. This is what electrical engineers do that work on the power grid. Okay? There's going to be some caveats. There's going to be some things that are waiting in the grass to kind of jump out and get us. So we got to be prepared for that. We can't lose sight of that, like under the hood, there's some stuff going on that we really don't want to look at. But every once in a while, it'll come up and we have to deal with it. Okay? So this is what we are going to do. Oh, let me show you this first. Just to help you understand how horrible it can be, and just give you some appreciation for what we are saving you from. This button. All right, this is a simulation of, in this case, just an AC generator that's been connected to a resistor. Okay, so if I run this simulation, what the graph is showing me is what the voltage in the resistor is over time. And because it's alternating current, we'd expect the voltage to do what? Alternate, right? Okay, no problem, Mr. Balogh. I can do a sine or cosine function. I don't want to, but I can do it. Well, okay, here's the problem. That's just a resistor connected to an AC generator. Do you see the symbol for AC generators, that squiggle, the sine function inside of a circle? So battery is DC, right? Just goes in one direction. AC, it wiggles back and forth. Okay, so what happens if we add a capacitor? So we threw a capacitor into this circuit, and now we turn it on. What's something that jumps out at you?
They're almost opposite.
Yeah, they're not doing the same thing, right, at the same time. They're not even doing the same voltage, right? But they're definitely not, like one has got a peak and the other's got a trough at different places, right? And now we're going to throw in a solenoid, an inductor. Okay? Right? Okay? Right? This is how bad it can be for real. And then, if you want to introduce phasors, there's your rotating vectors. Okay? That are describing this system. And where's the, oh yeah. And then you can see that the rotating vectors are mapped directly onto their sine and cosine functions, and my brain just exploded. Like it's bad. It's really bad, right? This is the real. This is what happens for real, right? In an AC circuit. What we're going to try to do is avoid that. Okay? We're going to avoid that by pretending that it's DC. Okay? So how are we going to do that? First of all, we are going to only do series RLC. You will not be required in my class to do anything with parallel connections when it comes to AC circuits. So our circuit, the most complex our circuit will ever become, is a resistor, an inductor, and a capacitor. Now, we will do variations on a theme of this. We can do one with like just a resistor and a capacitor and like leave the inductor out, okay? Or just leave the capacitor out, right? Like, and it doesn't matter what order you put these in because it's series, right? What's true in series? What's the same everywhere in series? current, right? The current through them. So it doesn't matter where. I can put the capacitor first and the resistor last. It doesn't matter, okay? For whatever reason, it's RLC, which is bothersome because it's not alphabetical order. But that's okay. It's reverse alphabetical order. So that's the first sort of simplification we are going to make, okay? We're only going to do series. In order for us to be able to treat this as a series DC situation, do you remember in a DC circuit, like what we had to do? Like if we wanted to know everything there was to know about the circuit, whether it was in series or parallel, what was like the overall approach? We had to combine everything down into a like single element connected to the battery, right? Once we knew that, we could then sort of go backwards to figure everything else out, right? We're going to do exactly the same thing. Okay? We're going to find the equivalent resistance of this circuit. Which should bother you. Do resistors have resistance? Yes. Do capacitors have resistance? Do inductors or solenoids have resistance? So how do you find the equivalent resistance of something that doesn't have resistance?
Find the resistance of the thing that does.
No. Pretend everything has resistance. Remember, I told you we're going to lie. Right? Okay? Pretend. Now, I'm telling you we're lying, right? We're cheating. It's a big wink, wink. It's like, right? This has resistance. But that's exactly what we're going to do. We're going to treat the capacitor as if it were a resistor. We're going to treat the inductor as if it were a resistor. And we're actually going to calculate those resistances. How the heck are we going to do that? We are going to use something called, don't panic, the root mean square value. Okay? Root mean square is a statistical method for averaging something that normally would be 0 and getting a non-zero answer. What's the average of a sine function? 0. It spends just as much time above the axis as it does below. So if you take all the values of sine and you average them out, plus and negative, you will get 0, which isn't very helpful. So instead, we do something called the root mean square. It literally means take your numbers, square them. What does squaring a number do if it's negative? Makes it positive. Then you take the average. Don't take the average first, because the average first would be 0. Square all the values first, take the average, and now because you're up by a square factor, what do you do to fix it? Take the square root. It's called the root mean square, RMS. Okay? We will never calculate it this way. I'm just giving you an idea, like statistically under the hood, something's happening that allows us to kind of pull this thing that's kind of like an average out. Root mean square values are not the maximum values you can have in a circuit. They are, V max over the square root of 2. There's always like a square root of 2 difference between what's going on. And, this goes for the current, by the way, too. When you are working with circuits and you are not told, like they tell you the voltage, whether it's DC or AC, you always assume, well in DC you don't have to make an assumption because it's just voltage. But in AC, if they just tell you 120 volts, you've been told the RMS value. Physics textbooks try to make this harder. They'll say the maximum voltage output by a generator is 170 volts. They didn't tell you RMS. They told you the maximum value, right? Okay. So divided by the square root of 2, which turns out to be, square root of 2 is like 1.7. And so I think 177 volts is 120 volts or something like that. You can do it in your calculator. But the point, I'm just letting you know, right, that sometimes problems will get very tricky. ChatGPT gets really confused over this, right, between max and RMS. It's not careful about delineating between them. But just, yeah, usually if you're just told an AC generator outputs 50 volts, what do you assume? RMS. It's RMS. It's just the RMS voltage. And everything I'm about to write down will be in terms of RMS. I'm writing the toolbox right here. Okay, this is our AC circuit toolbox. Okay, all right. So Ohm's law. I'm not going to write RMS anymore. It's all RMS. Is V times I times the equivalent resistance of your circuit, symbol Z, known as the impedance. Just hold on. It'll be okay. The impedance for a series RLC circuit is the square root of R squared plus X sub L minus X sub Z, C, quantity squared. Please note that the subtraction happens first before you square it, right? It is not XL squared minus XC. That's not what it is, okay? What are XL and XC? They're called reactances because students react negatively to, no, okay? There's the capacitive reactance, okay, which is the version for the capacitor, and then there's the inductive reactance, which is the one for the solenoid or the inductor. Here's the inductor one. This is 2 pi f times the value of the inductor. We haven't really talked about inductors. Inductors are fancy words for solenoids. Inductors have units of henries. I'm not joking. Usually millihenries is what they're measured in. Okay. Capacitive reactance, 1 over 2 pi C.
What is L again?
2 pi F C. I missed an F. It's the value, it's the inductance of a solenoid. You'll see it. It'll just be mentioned in problems. They'll tell you a solenoid has 650 millihenries. Okay. All right. I'm going to finish off the toolbox right now, just to get it finished off, and then we'll investigate its implications here in a second. Okay. Average power in an AC circuit, and we usually just say average power because power can be just about anything instantaneously in an AC circuit, is IV cosine of an angle, and you find the cosine of that angle by taking the resistance and dividing it by impedance. Please do yourself a favor here and don't ask why. Just don't ask why any of this is happening. Go with the flow. And again, some of you are like, I got you, Mr. Balogh, I've been doing it for 22 chapters. Okay? In other places, I would encourage you to figure out why, because the why is going to inform how to do what's going on, right? Here, you don't want to know why, because it involves differential equations and horrible things that are going on with sines and cosine functions. Again, remember the rotating vectors? That's why. Don't go there. Okay? Just don't go there. Okay? There's another way to get at this, what's called the phase angle. And it's this. I only give you these because sometimes you will be asked, like, what's the phase angle in a problem? There's no reason for you to calculate it. There's no reason for you to know it, but for some annoying reason, they'll just ask for it. Electrical engineers need to know this phase angle because it's important for them to be able to balance power on a grid. But we're not doing grids. Okay? And then we're going to just drop a final one. This is called the resonant frequency. We'll get to it in a little bit. Okay, so this, is the whole toolbox that you need to know for this circuit over here. In AC circuits, once you go to parallel, you have to rederive the toolbox. The toolbox is different for parallel, and then it's different if you mix series and parallel together. The thing that changes is the impedance. But again, we're not going to do any of that. We're just going to do series RLC. You will see in other sources, from AIs to other textbooks to websites and other things, YouTube videos, you will see them write this for the reactances. This is actually my preferred way to do it because this is how I learned. Okay, omega is 2 pi f. This comes back from physics 2a and the oscillating simple harmonic motion, where angular frequency and linear frequency are related to each other. Okay, it's basically the angular frequency of the circuit. Because one thing that an AC circuit is it's a mass on a spring. We studied masses on springs in 2a. This is the electrical version because it's just electrons bouncing around in different places. So there's the toolbox. How do we use it? The general approach is find the impedance first. Like impedance unlocks everything for you. It's finding the equivalent resistance, right? Impedance is the Z. Okay? So find impedance. To find impedance, what are you going to need to know? So you've got to go find XL, XC, and R, right? The reactive inductance, reactive capacitance, and the resistance, right? So you'll be using these, right? Well, to find those, you need to know the frequencies and the values of what's going on, right? Okay, so get your impedance. Once you have your impedance, you can find the total current in the circuit. And once you find the total current in the circuit, we can go and find a whole bunch of other things. Okay, so that's, again, the general overview. And I will now do a whole bunch of sample problems, of which I'm only going to have time to do the first one, and we'll just do more on Thursday. Okay, so I've kind of laid out the fact that what are we doing?
Cheating.
We're lying. It's called the convention. Everybody has decided that this is okay. It's not really what's going on, and that can bite you every once in a while. But it does make it easier to apply this to a grand scale in society and make power flow to all of your devices. So when tackling any kind of calculation problem, like hone in on things like, where did frequency show up here? It's like it's in those three places, especially here, right? Which means it's in here, which means it's in here, right? It's all over the place, okay? So identifying the frequency is really important, okay? So frequency, 100 hertz, okay? What's our voltage? 20 volts coming out of the generator, right? So what does my picture look like? Well, it's a generator, right? So we know that's a 20 volt generator at 100 hertz, okay? It's connected to what?
10 kilo ohm resistor.
A resistor and a capacitor. That's it. No inductor in this one, right? Okay. What do we know about the resistor? 10,000 ohms. What did I just do there?
Times 10 to the 3.
Times 10 to the 3, right? Okay. Get them back into original units. The original unit would be ohms. Okay. Our capacitor, it says 0.25, and what's the micro stand for? Times 10 to the minus 6 farads. Okay. And they want RMS current, right? They want to know the current in this circuit. That's what I'm looking for. Okay? What do I find first? Impedance. To find the impedance, do I know R?
Yes.
Yeah. Do I know XL?
No.
Yes.
Yeah.
What's XL?
2 pi.
If there's no inductor, what's XL?
Oh,
0. Right? If the inductor isn't there, it's 0. And then XC we're going to have to calculate. So what are we going to do? We're going to find the impedance. I put a line through my Z's because my 2's and my Z's look the same. So that's what I'm doing there. You can just use whatever Z works for you, but mine has it's not a physics thing to have that bar in the middle of the Z. That's a Mr. Balogh thing. All right. So this is going to be R squared plus XL minus XC quantity squared. And it always goes L minus C. Notice RLC, like it's in the name. Helps you remember the impedance, right? RLC. Okay, so now we got to, okay, so before we can do this, we need to find out what X, we know X sub L is 0. What's X sub C going to be? It's going to be 1 over 2 pi F times that thing, which is 1 over 2 times pi times 100 times 0.25 times 10 to the minus 6. I'm not sure I know what that number is. Yes, I do. It's right here. Past me, it was still awesome. Okay, so what I got was 6,369 ohms. Just throwing that in my calculator. Be careful with your parentheses. Okay, so writing down my impedance, I've got 10,000 squared plus, and then 0 minus 6,369 quantity squared. And when I did that, I got 11,856. I forgot to mention, how do I know the units of this comes out in ohms? Just follow the SI units. Frequency in hertz. Inductance in henries. Frequency in hertz. Capacitors in farads. If you go to the standard unit, you're guaranteed to have this come out in ohms. Do not try to figure out the units. Like, don't go to basic units and try to work it all out and see if it's an ohm. It's a rabbit hole you do not want to go down. Okay? Just put standard units in and it's guaranteed to come out in ohms. Okay. Now that I know my impedance, I can go ahead and find the current in my circuit. These will all be RMS values because it's AC. So I put in my 20 volts RMS. I put in my impedance, 11,856, and I get 0.00169 amps or 1.69 milliamps. Problem solved. What's hard here? So conceptualizing. I'm going to argue conceptualizing is pretty easy. Everything is a resistor, right? Turn everything into a resistor with the toolbox. Okay? Find the impedance, find what you need. Okay? So I think that's maybe the hardest part. It's true. But it's not that big of a stretch to say, well, everything's a resistor, just find it. What's hard is letting go and saying, but there's something real going on here and I don't know what it is. Correct. You don't want to know what it is. Just go with the flow. Normally I would say, just don't follow the rest of the society just because somebody says to do something on TikTok. See the cinnamon challenge or the Tide Pod challenge or any of those other, right? You normally don't do it. Here, the scientific consensus is, this is way better than doing it for real. So we're just going to stick with it. Okay? Once you can accept that everything's a resistor in AC circuits, it's really just a little bit of a puzzle to figure out what you're being asked to solve for. But generally find the impedance. That'll unlock the other things that you need to look for. We're going to do more examples of this on Thursday. Okay? And then we'll be done with all the stuff in this unit. And we will start preparing for the exam. I'll see you then.